And welcome to Climate Chat. I'm your host, Dan Miller, with co-host Leon Simons. And today we have kind of a little bit different, a little bit special. Oh, I'm hearing something. Sorry, I had another, our video playing in online there. Welcome, and we have something a little bit different. And Leon reviewed the European Geosciences Union 2025 Assembly, which contains all kinds of research on climate change of all different kinds. And we're going to get a little summary of highlights from some of the papers today from Leon. So Leon, welcome. And also you'll notice we have a little upgrade in technology for Leon. Sharper image and hopefully less issues with the video, and mine should be a little bit upgraded as well. So we'll see how all of that works. Leon, welcome to Climate Chat.
Hi, thank you, Dan. Yeah, and also thanks to some people supporting me on Patreon that helps to improve my my setup. So that's really nice to indeed that you can see me more clearly. That eventually my sound will be better. I tried some things but didn't work yet, but I'll get there. Yeah, so let's get to it. So the EGU is the European Geosciences Union, which is a union of geosciences, as the name suggests. It's climate scientists, earth scientists from all over the world who are part of this union, and there's about 20,000 of them, and that's also about close to 20,000 people come together, most physically, but also online in Vienna every year to discuss the latest developments in climate science or in earth science, and that's really extremely broad, of course. So you have climate modelers, you have ecologists, so you have I can go on forever about how many different people are looking at different parts of the planet. That goes from very small aspects to like different microbes or how they impact their regional environment to scientists who really look at the global picture, looking at either satellite data or ocean data on how things change. And today we can, I would like to just look at a small part of it, and over the next weeks and months, we can look at more different subjects to see to learn more, because I lost count of how many sessions I attended, and it's difficult to digest that all in one go. So unfortunately I wasn't able to attend personally. So I had to do it online because I had a death in my family. So that caused me to have to stay here in the Netherlands, and that caused me also that I wasn't able to attend, of course, all the poster sessions, which are a crucial also place where you have all these like hundreds of posters where every scientist presents their work with a very big poster where they highlight their main findings, and you can really discuss it with them in person. So unfortunately, I wasn't able to attend that, but I did because it was online. I could just sit here with multiple screens and also attend multiple sessions simultaneously, the live sessions, and that's of course not possible when you're there, and it's also very big, so it takes sometimes half an hour to walk from one place to the other. So that makes it there's also some advantage of being to attend remotely, of course. So let's get to the slides. Let me see. Presentation is this one. Yeah, there it is. So this is related to climate science. I think this is a slide a table which many climate scientists use in their presentations, just to show what drives climate change. And I've talked about it before. these are the forcing, so the effective radiative forcing. So what forces the climate to change? And you see the main greenhouse gases, which are CO2, of course, on top, and then there's methane and the other greenhouse gases, and ozone is more uncertain. These are the uncertainty bars, but it's also a forcing which adds also to this greenhouse gas forcing. And we are now at about the doubling. If you convert all these other greenhouse gases to CO2, we are now at about a doubling of CO2, as I've explained before. And then, especially what's often highlighted and what is crucial to understand is these aerosols, and I will be talking about that quite a bit today again. And here you see the big uncertainty, which is mainly related to the cloud. So there's a big uncertainty what the impact is of aerosols, which are these small, tiny particles. So gases are gases, of course. Greenhouse gases are gases. They have a very long lifetime in the atmosphere. They distribute very evenly across the atmosphere. But these aerosols are small, tiny particles that reflect sunlight themselves or absorb sunlight themselves and then scatter it, or they interact with clouds, and that causes a big part of the uncertainty, because these they act as cloud condensation nuclei, and they create these cloud droplets which reflect sunlight back to space as well. So that's caused a negative forcing, which causes the climate to cool down. Or of course, the net effect of all these forcings is positive, so there is warming, but there would be even more warming without these aerosols.
So a question for you there. We've seen this chart obviously many times. This is directly out of the IPCC, if I'm not mistaken.
Yes,
right?
this is an IPCC. This is the graph, and it's been in every main IPCC report. You see this graph. So going back to the start of the IPCC, and of course the uncertainties have been decreasing more and more, especially from the greenhouse gases. But the aerosol uncertainty has always been quite big. And this is an update which is still preliminary for 2024, because of course not all the data from 2024 is in, so we'll have to wait. This is from Chris Smith. I think his name is behind my tag there.
Okay.
But
I have a question though. The question is, we spent a lot of time recently talking about how Jim Hansen, and including you, in the paper Global Warming, the Pipeline, and subsequent papers from Hansen showing that ECS, or equilibrium climate sensitivity, is 4.5 instead of 3 degrees Celsius. In other words, for a doubling of CO2 using short-term feedbacks, some of them are quite long, but 1,000 years, but short-term feedbacks would lead to 4.5 degrees of warming if we happen to double CO2. So the question is this chart based? Does this chart include ECS? I think the answer is yes to that. And if it does, is it assuming 3? And if the number is really 4.5, does that mean this chart is wrong?
This graph it's not about Earth climate sensitivity or feedback.
Oh, just the direct warming from a greenhouse gas?
No, this is the forcing. So this is really everything before all these feedbacks happen.
Oh, it's before
and we'll get to that, because this is really this is the main area of discussion. Also, like, what is forcing? What are feedbacks? And how do you determine that, right? And it's and what do you present? Because some forcings are very different than others, and but I think that's a crucial question, and I'll get to that with I think my
we'll do it later.
My next slide. Let me see. Yeah, so I think this is here. You asked about James Hansen, his estimates, also about Earth climate sensitivity, and the effect of aerosols is quite important there, because if the aerosols are stronger, the effect of aerosols stronger, then more of the one we've seen is caused by a lower net forcing, because the aerosols were causing the net effect to be lower than it was when the aerosol effect would have been less negative. And then you see this I don't know exactly how to pronounce her name, but it's from Dr. Sky. And then Hansen, the estimate of the recent studies give radiative forcing, this from the International Maritime Organization, shipping emission reduction, sulfur emission reductions from shipping, and the recent studies give an estimate from these mainly these modeling studies give an estimate of about 0.1 watts per square meter, and that's from comparable to the CO2 increase of a few years. But then the summary is, I think, is important. Is so radiative forcing of shipping gap has large uncertainties, so that's important that to acknowledge these uncertainties, as I already mentioned before, and that's related to cloud adjustment. So what are the effects on clouds? The uncertainties on emissions, and then uncertainties, and I think this is often overlooked, the uncertainties in the sulfur cycle, which is mainly the natural sulfur cycle. So how much sulfur is already there in the background, because that the sulfur from shipping competed with the natural sulfur in impacting the climate. So that's really important, whether that's 10 million tons or 20 million tons of background sulfur from algae mainly, different, and it's called dimethyl sulfide, so DMS. So that really changes the outcome often, and also where this sulfur is being emitted, and that depending on the temperature of the oceans, on sunlight, on nutrients in the oceans, on how much wind there is, so how much what is in the ocean is blown into the atmosphere, and that's extremely uncertain, and also depends on the cloud. So there's some new research showing that if there's clouds and these particles or the precursors of these particles are taken up by the cloud, and then it says that the impact of internal variability is also uncertain, and that's an important point as well.
So this is saying that Hansen and Simons are saying that the impact of the shipping aerosol reduction is 5 times larger than the consensus, and 10 times larger than the minimum value. And I know that in
from simple models, I think that and I think I also asked this question during the session. I asked because they keep one thing they do is they keep the sea surface temperatures in the model. They keep it stable, so they don't let the sea surface temperatures increase when they increase the forcing and or decrease the sulfur emissions. And then so what happens then is you don't take into account the effect of the decreasing sulfur particles on the effect on the ocean warming, and how that responds to, or how for example clouds respond to that. If you have warmer oceans, the clouds respond by increasing in altitude, and then they also reflect less sunlight, and also the clouds evaporate faster. And that's how often the forcing is estimated, because if you really want to know the forcing without the feedbacks, that's why I get back to your question. What's done is the temperatures of the sea is kept stable, but and that makes to me that makes, in a way, of course, it makes some sense, and it makes sense if you look at greenhouse gases. Then it's easier to it's an okay way to estimate the feedback, and then they let the land heat up. But then this forcing is really centered over, of course, the sulfur emissions are centered over the ocean, and the oceans do heat up. So and then you start to get it's almost a discussion about language, or about interpretation of how much of this effect is indeed a feedback, or is a forcing, or is a feedback from greenhouse gas warming, or is it feedback from this forcing change, right? And it becomes quite complex, and then it's also you cannot really say anyone is wrong, right? It's like, okay, this is what they put it in a model, that's what, and they just present the output of the model. But then nature doesn't care very much about what your assumptions are in the model, or what. We really need to know what the impact is, and we can discuss whether this is a forcing or a feedback, but the impacts are
real.
the same in a way.
Right. And well, speaking of that, one more question about that is, one of the big feedbacks is water vapor. As the atmosphere gets warmer, there's more water vapor, and it's very powerful greenhouse gas, but it's not a forcing, it's a feedback. But as the ocean gets warmer, does that create, there's more evaporation from the ocean? Doesn't that create more water vapor in the atmosphere?
Also, because there's more sunlight hitting the ocean, of course, it also very much increases evaporation, because these photons, these light particles from the sun, which reach the ocean instead of being reflected back to space by these clouds or by these aerosols, they hit the ocean, and then they can help to evaporate the water molecules that are on the surface of the water. And then, so it's a crucial contributor to the increase in water vapor. And that's, of course, also considered a feedback.
It's a feedback, so not in this thing. Okay, let's keep going then.
Yeah, and then there were quite some. There were a lot of presentations at the EGU about observations as well, and I think that's where these. I think there was some almost like friction from my perspective, even when I couldn't be there, but I still saw this, in a way, friction between these models, which also show that there's, or they don't, but these IPCC models often show that there's not much going on, right? There's not much almost interesting going on. It's just somewhat linear, or maybe increasing a bit, and we've seen that a lot in the past years in more like the public discussions, where there was a question like, is there a runaway warming, or is there accelerated warming, and then the models say, well, in our model we see some acceleration, but it's not too much. But then the people who are looking at the observation data, which often modelers don't do that much, they really sometimes really have their head stuck in the sand or stuck in a model where they should get out of sometimes and look at the observations as well, and see how these observations compare to their own models, and why there's such a big difference in that. And Thorsten Maritzen had an interesting presentation on this, where he showed that the observation showed that the energy imbalance is rising faster than expected, according to these series of data. So this is the observations, and then here's also the observation of the satellite data, and you see the IPCC emulate, so where they reproduce the IPCC effects, and then you see that these peaks are much higher than what the IPCC shows. And then also the trend is it's more than double during the past two decades, than what is predicted by the IPCC. And of course is mostly based on models. And that's so climate models are incapable of reproducing the observed rapid rise. And currently we don't know why. So that's what Thorsten said. And
now, when he says that, they don't acknowledge that at least you and Hansen have explained why it would happen. And doesn't anyone read those papers and at least say,
right, well, look, we do not know why. He focuses on we don't know. I think that's, and then I think that's at the EGU or at the broader level. There's no certainty of what the cause is, right? And I think that you and I I think are inclined to be more certain that what the data is pointing at. And the more we look at the data and it's not going down again, especially regionally, of course, you can say, okay, this line is going down a bit from the extreme peak, so maybe it's not that bad, right? But if you look at the regional data, it's quite bad. And then so I think this is, I appreciate Thorsten pointing this out, that this, you know, taking this sentence aside, he does highlight that which many wouldn't acknowledge, at least until recently, and more are acknowledging this, that the NASA the satellite data is showing a very strong trend, which is beyond what the models show. What all these models, they don't show this trend. And that's, I think, and this is just one paper I saw, it was published a few days ago, also shows that, so it's not just the satellite data, it's also, this is based on global ocean heat content and sea level rise. So, and the title is Accelerated Ocean Thermal Expansion. So the ocean, when it heats up, it expands, and that it contributes to global sea level rise. But that all these findings, they convert it also to energy, because of course, if the ocean expands, you can estimate how much of that is due to thermal expansion and how much is due to melting of land ice, for example. And then, so they also show that the energy storage has tripled. So the Earth's energy imbalance, the rate of how much heat accumulates in the Earth system, has tripled in the past 30 years. So that's, and one I don't have the name here, but I'll get you that name later. One scientist at the EGU said that the Earth's energy imbalance gives you an indication of the rate of change about 20 years ahead of surface air temperatures, because there's a delay in all this heat accumulation in the system, and how long that takes to translate to the make visibility in Earth's surface temperatures, because there's much more variability in surface air temperatures than there is in global ocean heat content accumulation, because that's more that increase is more gradual, and then and it makes sense, of course. We had, of course, the El Nino, where we predicted already before it happened that this would show a big spike in global temperatures, because we were already paying attention to the Earth's energy imbalance back in 2020 and before 2023, and we were already, Hansen and I and some others were already predicting that if we will have a strong El Nino, we will see a big jump in record temperatures in the years where this El Nino will take place. And even we didn't have a very strong El Nino, we had a moderate El Nino, we did see this enormous spike in temperatures. So I think that's important to show that, you know, all this focusing on surface air temperatures, which is only a very small part of where all the heat goes, is one of the reasons why many Earth scientists are still a bit hesitant to see or to conclude that acceleration is really happening. But if you look at really the energy imbalance, you see that it's quite clear, as this showed and as my previous graph showed. And this is also wait, let me see. This is also quite an interesting graph. Interesting figure from a presentation on the decreasing albedo. Wait, let me 1 second. Or do you have any questions on the previous points?
No, it's good. Let's keep going.
Okay, so The Helge Gusling gave this presentation on the paper is called "The Recent Global Temperature Surge in 2023 Was Intensified by Record Low Planetary Albedo." That's the name of the paper. He presented, and it was published, I think last year, and end of last year in December, and that showed that about 0.2 degrees Celsius of warming can be explained by a decrease in albedo. And then, so the point he made here is that all these questions about if it's just internal variability, and he didn't make any conclusion of what caused in this paper or at this presentation. He didn't give a strong conclusion on what caused the decrease in albedo, which then contributed to the record temperatures in the past 2 years. Focus was in 2023, but he did make this point where he said that, you know, if we keep getting this question, like, is it just internal variability? And this cartoon shows explains it a bit. So it says, so this person died of natural causes, because people have always died of natural causes, right? And it's in a way somewhat of a stab at this question, where many keep saying, oh, it might just be natural variability, or the null hypothesis is that it's natural variability. But yeah, we do see what he called this very strong increase in global absorbed solar radiation, and also the strong increase, especially in the northern hemisphere mid latitudes, of this increase in absorbed radiation. So less sunlight being reflected back to space, which means that more sunlight is being absorbed by the oceans, especially, is quite a strong indication that it might not just be a natural cause, right? And
yep,
I think that's where the modelers and should start paying more attention on this data, and also trying to really not just see what the temperatures the models produce, but also at how much absorbed solar radiation there is in a model. Because if you could get, for example, the right outcome, you can say, okay, look here, 2023 was quite warm, but there's some dots that are higher, so it might just be natural variability. But then if you look at all these other points of evidence, because this is just really a very narrow way to look at the product, what your model produces, right? If you start looking at the other aspects, you might be right for the very wrong reasons. And then, yeah, this is, I looked at it again after at the data, the regional data, where we because that's in line with the presentation. I just show you this.
no, that doesn't work.
Sorry. Sorry.
Yeah. Sorry, I tried to make it bigger, but it didn't work. Cut it off.
Yeah. So what Helge Gusling, the region where Helge Gusling and his colleagues were highlighting on for the northern hemisphere mid latitudes was these latitudes from 23 degrees north until 55 degrees north, and then global. But here I focus more on the oceans, because there the signal is even stronger, because if Eurasia, of course, there's less shipping happening there. So I think, and there's, if you exclude that, you see that the signal is even stronger, and you see a very strong increase in how much sunlight is being absorbed in this region. See, there was not so much change, and then it started to increase, and then that might partially be due to natural variability in the beginning, but also because China was starting to desulfurize its coal plants very rapidly. So there was also quite a bit of quite some presentation on that at the European Geosciences Union, and there was also around 2015 there started to be regional emission control areas for this sulfur from shipping. So you saw, and then you would assume that this could have some impact on how much sunlight is being reflected and thus absorbed. And then we see this big
so this
increase
black line,
happening.
just
Sorry?
to help everyone understand, that is
What
how
we-
much sunlight is being absorbed by the Earth, and it's not doesn't have anything to do with greenhouse gases, which allow sunlight to pass through, but it traps the heat on the way out. The heat on the way out is the red line. So the black line going up is
It's a
not
change.
explained by greenhouse gases. It's explained mostly by aerosols. It could be a little bit of the sun being higher in its 11-year cycle, I guess, but that's a very small effect. Is that right?
Yeah, so if you just would have greenhouse gas increase, and that would be the cause of warming, you would expect the red line to go down.
Right.
But now you see, even if there's warm, because then that would cause more heat to accumulate in the system because there's less heat being radiated to space. But you see a big increase. The red line shows outgoing long-range radiation, so heat being radiated to space by Earth. You see that there's quite an increase, and it's the same is happening globally. This is regionally, but the same is happening globally. And then you have some people saying, okay, that disproves the global warming hypothesis. It has nothing to do with greenhouse gas. That's not true, because without the greenhouse gases, this line would be much higher, because this is caused by, if the Earth heats up, it radiates more heat to space, and that's called the Planck feedback. We've discussed it before.
Mm-hmm.
But
Right.
then the black line shows absorbed solar radiation, the change since 2004, where you see that this is increasing much faster than the red line is increasing. And that's because, of course, the increase in greenhouse gases, keeping this gap wider than it would be without this increase in greenhouse gases, the water vapor feedback, reduction in clouds, and reduction in aerosols. And how much of the reduction in clouds is caused by a reduction in aerosols, that's quite uncertain. But this is a smoking gun, if you would have, or the knife in the back, right? This is a clear indication that there's likely something happening, and this increase of it's 4 watts per square meter. That's as much as the effect of the greenhouse gas effect would be of doubling the amount of CO2 in the atmosphere.
Right. It's a huge
globally.
amount. Now, some
So
people might say if it was the shipping regulations, that would kick in 2020, which it certainly did seem to increase starting in 2020. But actually, this IMO regulation, didn't it start in 2015? Like the first part of it?
Yeah, so the first part indeed.
And that's when this thing started separating out.
Yeah, so then that was around the coast of North America and around the North Sea. These are called emission control areas, where in these regions they enforced the reduction in maximum sulfur fuel content in the fuel ships from 3.5% to 0.1%. And then that happened in 2015 already. But then in 2020, there was a global reduction from 3.5% over the rest of the oceans to 0.5%. So on January 1st, 2020, that came into effect. And you see then that over this, and then so what we said, and we looked at model studies before that have been taken before, like from 2013, from someone from Partanen et al, and some other studies showing quite a strong estimated impact of these regulation changes. And then you saw that but then of course it was just some model outputs, and there were also models which showed a small increase. So we didn't have the data yet. Now we have 5 years of data, and we see that it's still increasing. Of course, and you would expect that there to be some lag and also from the cloud feedbacks, but it keeps increasing more and more, and then we keep hoping, of course, that the data is wrong. But now we also see the same happening to the sea surface temperatures, which are rapidly increasing in this region, and also the Mediterranean. And then now we start seeing it in global temperatures reaching these extreme record highs. So the more data comes in, the more it looks like that there's really a very strong forcing and responding feedbacks regionally and globally of this shipping emission changes.
Now, one thing we learned here on Climate Chat, we're talking to George Salutis, is that warming also decreases clouds. We're not talking about stopping shipping, which decreases aerosols, which directly stops clouds from the shipping trails. We're talking more globally, as the temperature warms up, a trend is, and there was a big question mark for climate science, do clouds increase with warming or do clouds decrease with warming? And the data seems to be showing that the clouds decrease. So could part of this continued continued increase in absorbed solar radiation be due to clouds decreasing after the warming caused by the shipping change?
Yes, and then that's what I mean by feedback. That's cloud feedback. The cloud. So indeed, these oceans heat up, and then because it's warmer, the air can also hold more water vapors, and then you see the clouds evaporate, or you see the altitude increase, and then so there's less cloud cover, and because there's less cloud cover, there's more sunlight being absorbed by the oceans, and then the oceans heat up further, and then there's more water vapor again, and this hot water vapor also keeps more heat in, and there's less condensation, so less cloud formation because it's warmer. So these feedbacks take time to come into effect because it takes heat for the ocean temperature to increase. It takes a lot of heat to increase the temperature of ocean water because of it's called the thermal the thermal heat capacity of water is very high. And of course, there's also quite a bit of mixing. So it takes a lot of heat to increase the temperature of water by a large amount. And of course, there's a lot of water out there. The oceans are very big. So you need a lot of, what do we have now? Over 10 Hiroshima bombs per second's worth of heat accumulating in the oceans, right? So it's hard for us, or I think impossible for us to grasp how much energy this represents. Right. And then even with that rate of heat accumulation, it still takes a long time for this to translate to higher temperatures and for these feedbacks come into effect. A long time for us humans who keep looking at our watches, but on a geological time scale, it happens in an instant, of course, and it is really unprecedented rate of change.
Yeah, this could be a chart you could be watching in the for natural causes happening over 20,000 years or something. We're watching it happen over.
Yeah, can I stop sharing and I'll upload the other graph and then I'll upload it.
Okay.
Yeah.
I think how about your video? Your videos for later.
Yeah, maybe. So I also gave a presentation. Or I was planning to present the research as a poster, and I'll present our findings at the whiteboard behind me, where I was working on the poster, and my daughter helped me a bit on the visuals. So it's an interesting research we are doing with my friend and colleague Yandu Fournet, which builds on the findings in global warming in the pipeline led by James Hansen, where we show that there's the greenhouse gas forcing of the past 130,000 years. So you can, and let me get that, because I think it will be good to show you. And it's always quite interesting when I share these graphs. This one I also shared it on LinkedIn, where it got like 80,000 views, and it's always quite surprising how much interaction there is at different fora. You know, if you go to the EGU, of course, there's 20,000 people there, but not 20,000 people will see your work. And then sometimes if you just post it on LinkedIn, you get much more views than you would ever get on at the EGU. So I think that So I'll just show you this graph now, and I'll.
Okay.
We've discussed it before, and I'll. Can we show it now? This is how it works. Yeah, great. So this is what I showed I posted on LinkedIn. I was planning to show it at the EGU, and this is the 130,000 years of greenhouse gas forcing, and then the unit is converting it all to CO2 equivalents, as if if all the other greenhouse gases stayed the same from 1750 on or backward. So that translated as if all the changes that happened are then converted to CO2 change. And then we already have a doubling of CO2 equivalents. But then if you look back, quite strangely, we didn't even go back to half of the concentration we had in 1750. So we already sorry, here it is. I was
now, however, there was methane, and methane's about 1,900 parts per billion, or 1.9
now it is,
parts per million now, but it was about 0.7 pre-industrial. So however, that gets mapped. So we weren't really at 280 on a CO2e basis back pre-industrial, right?
No.
I guess this is everything, right? This includes all.
Yeah,
that.
no. You assume that So what we do here is we look at the concentration of all these greenhouse gases in 1750, and then the changes that occurred. So this is based on ice core data.
Yeah, right. But that's the going back to the Ice Age and everything.
Yeah, so you go back in the Ice Age, and then to the Eemian, to the last warm period, when sea levels were 5 to 10 meters higher than they are today. And then, so what we see then is that, sorry, let me explain, because it might not be very clear. We would assume, of course, we look at how these methane and nitrous oxide and all these other greenhouse gases change. But then we pretend like they don't change. But how much they change, we convert that to CO2, to how much CO2 would have changed if to produce the same amount of forcing change. And that forcing change is in watts per square meter, but here we convert it to CO2. Okay. And then you see that even taking that into account, taking this methane and nitrous oxide decrease into account, we don't reach the half of the 280 parts per million yet.
It's like 180 down there or something. The minimum.
We reached more than a doubling already now because of our emissions in the past 270 years. Mm-hmm. So, of course, there's other things involved here. The more ice and that has melted, and so there's more involved than just this. But just looking at the greenhouse gas forcing increase, it's mind-boggling what we have done in this very short amount of time, looking at from a geological perspective.
Right. As I said, normally you would be looking at 20,000 years. Exactly what we're looking at here is the first drop to that minimum is about 20,000 years ago, when the level was about 180 parts per million. And then it took 20,000 years to go up to 280. And then we made it go up to essentially double that in 100 50 years or so. Pretty crazy.
Exactly. Most of the greenhouse gas emissions happened in the past 150 years, indeed.
Or most of it happened in the last 50, right? I mean, in terms of the quantities. Yeah. Wow.
Yeah. And that's quite that's very important. And then I can talk a bit more about this now, but I think then what we estimate is that part of this increase is mitigated by air pollution, and already for 6,000 years, and it might be hard to believe that we have been capable of reducing or being capable of emitting these aerosols already for thousands of years. But I'll show you the video. And
so this is Madagascar.
How that's being done now. So this is Madagascar. Let me start.
So this is Madagascar. So in Madagascar, people are still burning their mountains down for the cattle. You can see it here. So there's very few trees because the mountains are burning. So they burn down the grasslands, they burn down the trees, and then the cattle can come and eat the young grass,
which starts growing again after the rainy season.
When you know that this should all be covered by trees without humans, it's quite a scene.
Pastoralist farmers have been turning biomass into CO2 and aerosols like this for thousands of years.
So this is Madagascar.
Oh, here we go.
Yeah, so it's and that's not just that's for cattle, but it also happens with agriculture. You see that happening everywhere in the world. But for example, now also before the rainy season in India, they start burning the crop residues, and then if you remove this crop, of course, then you give back the nutrients to the soil. You also remove the plant matter, which gives the new seedlings what do you call it? Access to the sunlight again, and of course to the rain. So there's a lot of, and that's of course very short-term focused from these farmers. But of course they want to produce food and fast, and these are the methods they know and use to still, and as they've been doing for thousands of years, burn their environment in order to create agricultural land, to refreshen the nutrients, and then and there's quite some studies showing, and of course there's also skepticism on that this has increased already the greenhouse gas concentrations of CO2, of course, but also the increase in rice production has increased methane concentrations in the atmosphere over 6,000 years, and that contributed to the greenhouse gas forcing. But the climate has been very stable over the past 6,000 years, and that's where in our paper "Global Warming in the Pipeline" we presented this theory that the forcing has been kept more stable because of this increase also in aerosols, which was both about half a watt. Greenhouse gas increasing by about half a watt per square meter of forcing, and aerosols decreasing from 0 to minus half a watt per square meter of forcing. And that evens each other out, and then you have very little change over time.
Well, let me repeat that, because that's pretty important. There's a general assumption in climate science that we started fooling around with the climate at the Industrial Revolution. A little bit, tiny bit before that, but basically at the Industrial Revolution we started, burning coal and stuff, and putting greenhouse gases. But what you and Dr. Hansen are saying is that it's possible, actually, that we started this process 6,000 years ago by humans playing an outside role in the climate by doing a few things like releasing some CO2 by burning, clearing land, but also rice cultivation, which releases methane. And then also offsetting that with the burning everything and putting aerosols up in the atmosphere. And back then, by the way, pristine atmosphere, nothing else there except for, well, forest fires and things. But, and therefore having a countering effect and keeping a very stable. So humans played a role in keeping that climate stable for 6,000 years until we just went crazy with our release of greenhouse gases. Did I summarize it pretty well?
Yes, and I cannot like emphasize enough how big the impact was of humans, and it's hard to imagine, right? If you think about it, how like there's only a few million, and we don't know exactly, of course, how many humans there were, but it's hard to imagine that. Of course, now we are with 8 billion, and so still some people are skeptical about how big the impact of humanity is on the planet. But then if you go back to pre-industrial population levels, it might be even more difficult to realize. But even before these 6,000 years, humans made many of the big mammals go extinct.
Mm-hmm.
Hunting the horses of the Americas to extinction. Hunting buffaloes or of course the mammoths and like countless species. The big sloths of and so there's so many species that already were made extinct because of humans. So you could also argue that in many ways human, like what's called the Anthropocene, already started way before 6,000 years ago. So the effect of humanity on the planet started way before 6,000 years ago.
Well, one fact that people don't realize is that, I mean, already today, about a third of all the non-ice covered land on Earth is used for meat production for humans. I mean, well, that number alone is just absolutely mind-boggling. That's not, it's grazing area, that's growing food for animals that we eat and that kind of thing. It's pictures of what you just showed. I mean, the video you just showed, all of those things. And that's been happening for 6,000 years. It's not something that just happened today. Although with 8 billion people, we are accelerating it now and eating into the Amazon, which decreases rain in the Amazon, which helps the Amazon become less stable and all these things. So
yeah,
pretty mind-boggling. It is all mind-boggling.
On that as well, but I think that will take too much time to elaborate on all that.
All right, let's keep going then.
Time for another day to I think I could show more presentation, but I also don't know which slides I'm allowed to share. What I shared now was from researchers that clearly indicated that we could use and share their work. So what an important research that was discussed was on the aerosol, the effect of aerosols again on the monsoon system, and that's also really crucial because the monsoon rains change, especially because of these aerosol changes. The effect of aerosols on especially the Indian monsoon is even stronger than the effect of greenhouse gas warming, and that's not even a big there's not even a big debate about that. There's just a bit of the uncertainty of how strong that effect is, and that's quite important, of course. So if India starts to reduce its sulfur emissions as it has been intended to and has been postponing for a while, we're now reaching the point where likely it will start to decrease in the years ahead. And of course, the shipping emissions are already decreasing. So I think India should really get ready for rapid monsoon changes.
Mm-hmm.
And when we discuss all this on a scientific level, it's it's hard, and I think that most scientists are not really good at communicating this urgency, especially something because they've been discussing this for years. Like, it's not for them, it's also not new. It's like, for them, it's just like, this is a scientific finding. It's very worrying, right? But it's, they don't use the voice of someone who is worried. Like, you say, wake up, people! India's monsoons are changing. You need to get ready, right? But that's, yeah.
Well, the
Scientists
heat
don't
wave,
talk like
the
that.
big heat waves are hitting Pakistan and India right now, and it's early in the season to have such crazy high temperatures, and that's early in the season, so it's going to be rough.
Yeah.
And then, as you mentioned, Mediterranean changing, and so these things are. The thing about aerosol changes, I mean, we've talked so much about this, but it's probably worth repeating. When you put up CO2 in the atmosphere, it lasts there for hundreds to thousands of years. And it does have this time frame where it does have this impact where you get some of the impact right away, and then over the next 100 years, and then over 1,000 years. But when you change, aerosols last in the atmosphere for about a week when they're in the lower atmosphere. About a year, by the way, when they're in the stratosphere. But in the lower atmosphere where you breathe it, and by the way, it's deadly to breathe. So you stop something, like you stop shipping emissions, or you put sulfur scrubbers on your coal plants to improve the air quality for the people who live nearby. That has an immediate, like a month later, the aerosol concentrations are far different than they were just the month earlier. And that has an immediate change, as we saw in 2023, 2024, from a shipping change that happened in 2020 and was hidden for a couple of years by a La Nina. And then as soon as La Nina went away, boom, you saw it. So people are not ready for these. And people are expecting climate to change very gradually over, a little change over over a decade. You can kind of notice the change, but that's not what's happening now. We're making changes, both bad changes to increase greenhouse gas emissions, and then the cooling, we're cleaning up the air because it's bad for human health, cleaning up the air, and this is happening in real time. It's something that's we'll be able to see the impact on the Mediterranean from the shipping change that happened 2 days ago, I guess. We'll be able to see it this year, like in the summer. We'll be able to see that impact.
And I haven't seen a single journalist cover this, like in the main in high level media, and that's not even on just to present the health benefits for the Mediterranean region, right? There's hundreds of million people living in this region. So we do this. This regulation is there to improve the health of the people, where the sulfur emissions from shipping in the Mediterranean are decreased again by 80%. So from 0.5% to 0.1%, and then it's not even celebrated. The health impacts are not even celebrated. The environmental benefits regionally are not even celebrated in the media, let alone that the potential climate impacts are being discussed. It's like I don't know why. It's like it's a subject that's like doesn't get any attention whatsoever, and I think that's quite worrying, because people really need to know about these rapid changes, and the models of the studies, many studies looking at regional change, don't take this into account. Europe, the Netherlands, for example, and much of Europe has an increase in sunlight reaching the surface of 15 watts per square meter. Well, this 4 watts is already a lot in this large region. It's already really a lot. But Europe, it's much more. Since the 80s, it's 15 watts. And then the models don't take that into account. And like, it's like really
15 watts.
15, yes, 15. And even regionally, it's even more. But this is for the Netherlands and for large regions in Europe.
Wow.
But there's certain areas where it's, I think, like 20 or 25 watts per square meter. So, and that's crazy. So that increases cancer because there's more UV radiation reaching this. And like we tell our farmers, and we have these like magazines for farmers where we tell the old farmers who are used to to the high level of clouds and a high level of air pollution, that they should start using sunscreen because the UV radiation has increased. But if we look at it, like for the regional climate, we also should tell people, or we should inform them about adaptation and to these rapid changes that are already going on.
Mm-hmm. Very good. So are we ready for questions?
Yes. I think I have some other subject, but let's discuss those another time.
So let's see if we got Tracy. Stacy is ready here. Okay. There we go.
Yes, Stacy.
I
Hi,
was
good
talking
to see
about
you
somebody
guys.
Tracy yesterday, so that's why.
I understand. Great to see you guys, and thanks for bringing this to us, Leon. I was hoping that for my benefit and maybe some others that are watching, you and Dan, whatever, could go over a time scale effects sort of tutorial. So what are the things, like, obviously I follow what we have done as humans is just, it's like that this is, we really did quite a job, yay us for warming up. How else could this have happened, right? But what are the things that take a long time to reach? What are the things that have very short effects on climate? And what are things that there's like a delay? Like we do it now, but we don't see anything happening for a long time. I'm just could use a little straightening out on that because we've gone back and forth over timescales.
Yeah, so the changing the air pollution, that has really like direct effect within days, within weeks,
Mm-hmm.
and that's, yeah, I think everyone could see that during the COVID years or years, where you saw that if when the plane stopped flying, you could see the skies turning blue. And then you could already also see when the industry was like phased down because people couldn't go to work for a while. You can also see that the larger regions like India was having again clear view of the skyline of what was it, the Himalayas. They could see the Himalayas again, and of course that's in a way somewhat anecdotal, but we saw it all around the world, and the data is there. And India also has data where they showed it. I think it's about the same amount, like 15 watts per square meter of, and that's day and night average. I should point that out as day and night average increase in sunlight reaching the surface of the North India during these lockdowns. So that's an enormous increase in sunlight reaching surface and in heating, and those are these are rapid changes. And of course, if you look at CO2 and other greenhouse gases, those build up over time because because they don't rain out as fast as this air pollution. So there's this accumulation every year. You add like 20 or 30 or 40 billion tons, and that accumulates, and that is distributed around the planet, and then the concentration keeps increasing more gradually. And that's with feedbacks, it's somewhat the same. It takes time for all this water, the temperature of the atmosphere to increase, and for these impact, the water vapor to go around the atmosphere and to increase, and then for the water vapor feedback to come into effect. So these feedbacks takes more time as well. And of course, then you have the sea ice, which is also, and the snow cover, which is also based on how much heat is there in the system. It takes a lot of heat to melt ice, much more than it takes to heat water by a few degrees Celsius. It takes a lot of heat to melt all the ice on land. So that could take thousands of years, right, to melt all of Antarctica, which has about 70 meters, 50 to 70 meters of global sea level rise stuck captured in all that ice. That will take thousands of years. So there's all these different, indeed, it's a crucial question where how long it takes for all these things to materialize. And of course, if you have less ice, that will absorb, and then so the full feedback of absorbed solar radiation from all these feedbacks of melting ice, etc., that could take up to thousands of years. But the first impacts will be felt very rapidly, and then the slower things will take a long time to materialize.
Can I just say it back to make sure that I've got it? So when we decrease pollution, we are removing our sunscreen, our visor, our parasol, whatever, and we are getting more heat coming in. And we did this by reducing things like reducing pollution, which was witnessed very visibly, as you mentioned, in the pandemic. We have gone further, or it was also at the same time was the shipping rules to improve the fuel so that we could improve our health and for the health of all life forms on Earth. And now we're going further, like the regional Mediterranean rules will come into effect. So we're removing our sunscreen, our visor, our parasol, etc. At the same time, we clever monkeys have been burning fossil fuels, which have been building up because the CO2 doesn't go out of the atmosphere. And so the effects of that, when we, somebody powers on their car or, whatever whatever, all the things we're doing to create CO2, the effects of that are not felt immediately, but it's the cumulative effect over time. We've been doing this for at least 150 years, burning coal, burning wood before that, and now fossil fuels, et cetera, et cetera. So all of that is built up, but we've had our sunscreen, and now we've been peeling that away because that kills 1 in 5 humans a year worldwide. So
about 8 million a year.
8 million
people. 1 in 5 deaths.
1 in 5 deaths. Yeah,
about 8 million people
1 in
a
5
year.
deaths.
And someone said that's
annually.
not 8 million. I looked it up. That is about 8 million.
It is. Yeah. Yeah. So it seems like we have been at this for a while. As we have been, our activities helped save the climate very, very early on, long ago. We would have gone into an ice age if we weren't farming rice and doing all the things that we clever monkeys were doing. But then we got to a point where it was like, oh, look at this thing, we can burn it and it makes stuff, like it can make us do more. Like, how cool is that? And we did that, and then we found other things to burn and whatever, and we're burning and burning and burning, and it everything's out of whack. And so how do we get people to understand that the burning and burning and burning and burning and burning we've been doing, and the sunscreen removal that we are doing for excellent reasons, are now colliding? And what do we do to solve that in an efficient manner? Change our behavior or apply some sunscreen? I don't know. Do you have thoughts on that?
Sunscreen, solar, sunlight reflection methods, emissions reduction, carbon removal. I mean, things we can do. We're just choosing to do nothing so far. We're just going along for the ride to see what happens. So I guess we're about to find out.
But
the basic answer to your question is that it can happen very, very rapidly. I mean, some of it, and as we saw, the last 2 years have been incredible example of things that the climate scientists said we can't explain it, but except for a few. And the
only other one was the 1 in 512 years that man said, or something like that. Like,
I don't even think that. I wouldn't read too much into that in the comments.
Okay.
I mean, if you let's find a reference from man himself rather than relying on a comment like that.
Yeah, and I think that there was I don't know what this relates to, but there was indeed a paper that said like there's a 1 in 512 chance or something that 2023 could happen naturally. But then I would indeed refer to the cartoon or the knife in the back and the guy saying people have died of natural causes, so this is a natural cause.
Yeah.
Very good.
So see, we're going to go to
and then come back. Yeah.
Eli, and then we'll
Thank
come
you.
back to you, right? Yeah. So
Yeah.
Eli, I believe you are on.
Yeah. Hi. Thanks.
Yeah. So what's your question?
Well, first, a couple of comments. The very first one, going back to what Leon was just saying about the gradual changes over thousands of years. That's the 10 degrees centigrade that Hansen and in the preprint or in the paper that you were on, we're talking about. Whereas we get the 2 to 4 much sooner. So that's the abrupt part, and then there's the long-term stuff over thousands of years.
However, to be clear,
so
Hansen clarified that later, saying that's not a prediction, that's a scenario. The point was, I mean, just like ECS is, if we double CO2, you get this temperature. Now, you don't have to double CO2, but that's what happened. And he was saying, if I believe I'm remembering this correctly, that if we keep forcing constant for the next thousands of years, then you're going to get 10 C of increase. However, we will not keep it constant. That's almost for sure. First of all, now we're increasing it, so we're making it worse. But then again, if and there's a mass extinction event because we don't get our shit together, then then it could fall naturally over time. So it's just a scenario. You hold that constant. This is the temperature you get, and it's a useful metric. But I think we have to be careful in implying to people that hey, 10 C is inevitable or something. It's not inevitable. It's all up to us at this point.
No, we can do much worse. That's also, it's
and
both.
We're making it worse, I should point out. But
I think that we're doing it like we could do both. We could make it much better, or we could make it much worse.
Right.
And for now, we're doing a lot to make it much worse. And personally, I've talked with you about it before. I don't think the focus should be too much on the 10 degrees Celsius. There's a lot that's very interesting in the global warming in the pipeline paper. I'm pointing one thing out because if you understand how these aerosols have been helping to stabilize the Holocene, which is the period where agriculture developed, where humanity developed. 5,000 years ago, we were building pyramids in Egypt, right? So this is the period where a lot, like most of written history, happened in this relatively stable global climate, and we should really learn to value how important and how crucial it is that we keep it that way, and learn lessons from the past of how that was possible, and one thing is we shouldn't increase greenhouse gas concentration so much that most of life in the oceans is impossible, right? So and while we are doing that, we might want to also learn from history and from the present that we could also reduce harm if we choose to do so. But then we have to start taking the forces that drive climate change regionally and globally, to take that very seriously and act accordingly. And that's really not what we're doing. It's almost impossible to even discuss these things.
Yeah. So the question it relates to things that you mentioned at a couple of points, how models are not representing things that are clearly happening, like the change in sea surface temperature and the time constants of response. So I'm kind of wondering what you think of the analogy of these climate or the overall thrust of these climate models that has really underrepresented what we're seeing coming to pass. as an analogy to the innovative financial products with some buried assumptions that led to the Great Recession, where there were some really bad assumptions in some primary things, and then people built on top of them and on top of them, and lo and behold, things broke down in a rather rude and surprising way, at least to many people who were involved.
Yeah, I think it's a very good analogy. What's the name again of the film by Adam McKay? Sorry, you're muted then.
Don't Look Up.
Yeah. No, that's not what I was talking about. But I meant the one that's about the bubble, the Big Short.
The Big
Sorry,
Short.
The Big Short. Yeah, you saw these, like, there were these guys that were looking at the data. They were looking at and they were going to these villages or these towns where people were getting a mortgage of like, or they were getting 10 mortgages. Like there was this like prostitute or pole dancer, I don't know, getting who had a side business of renting houses, and she had like 10 houses, and no one was checking her cash flow. She could just like get a mortgage on a house and rent the house again. And they were looking at all this like real world data to see what happens in the real world, and they were like, this can't go on forever, so they started short selling it. They were like betting on the housing bubble, and of course you had some other circumstances happening as well, where you had the oil price going up, because it was like, I think before all the fracking happened, so there was the more demand than in fossil fuels than the supply, and then of course the gas for the people got it more expensive. Then of course the increasing energy prices translates all the way into every aspect of the economy, and then the bubble burst, and then of course these guys who bought into this bubble, who got very rich from all these people losing their homes and stuff, but they saw it happening because they were looking at the real world data. They understood what was happening in the real world, and that's what we are doing. And I'm not betting on it. I don't know but if I could, maybe I should bet on the collapse of the climate system in a way where all this, because the data strongly shows that we are not including crucial aspects of the Earth system in many of the models, and that we will have to suffer the consequences in Europe, where we are dealing with the desulfurization on land and on the seas and oceans around us. But that's happening everywhere, in India and in Africa, in the United States. We better get real about this, and yeah, please let me know if you know where I can short all this.
Yeah. By the way, so speaking of that, Jim Hansen made a prediction, a very specific prediction, that 2025 will be about as warm as 2024, even though there won't be an El Nino. So there is no real explanation for that, unless you folks are right, which I believe you are, but of course. And so far the data, I mean, I guess April data is already there, and it's so far true. What will climate scientists do at the end of 2025 when there is no explanation? I guess that's one question. And then also that picture, with the different colors showing the temperature of the ocean at different latitudes, and then showing that there's this new El Nino type warming happening in the North Pacific and North Atlantic. What do people say about that? I mean, you can see it. It's data. And are climate scientists just ignoring that, or when they just say, hey, we don't know what's going on?
They're doing exactly what they are doing in the Big Short. Like, you know who I am? I know everything. I'm like, who are you? You don't know. Like, it's the big bank, like all these big banks are like, I'm a very big bank, and now we have, like, I'm representing the IPCC. I'm a co-author of the IPCC. You're not telling me shit, but they are. they are not even responding to the data. This is one IPCC author was also like saying, yeah, look at the next, when we'll have a heat wave in the Mediterranean, people will blame the shipping again. It's like, yeah, it's like they might, right, and they might be right, because it's like because then there's indeed like one study showing there might be a very small effect of the shipping emissions, and then but they don't look at the data. They don't even mention sea surface temperatures. They don't even mention this NASA series data. They don't even cite James Hansen in his new paper. It's just like they're gatekeeping the data. They are ignoring the data, and then they keep. And I don't know why. It's like you have to ask them themselves, and they will. So like, some people like, and of course scientists like, yeah, they're not very good communicators often. So,
well, by the way, I think we have a bunch of
and some people
the
just
trouble
like
is
stuck up and they couldn't really respond to my questions. And
Eli?
also at the EDU, it's and I don't want to offend them or something, but it's, you know, it's hard. It's really hard because we don't have all the answers, right? There is big uncertainty. It would be much nicer if you could just like wait 20 years until all the data is in, and then we can have a nice civil scientific discussion.
Symposium.
But we don't have that time. We need to prepare for all these rapid changes.
Yeah, and that's exactly it. The problem is that nobody can bail out the climate when we find out that the assumptions have made the house of cards collapse.
Yeah.
Okay. So let's go to some of the YouTube questions, or some of them relating to what we're talking about.
Yeah, we have to ask Clean Titan's question because he asked it about 10 times. Although I would shorten the time frame. He says what cities will be underwater in 100 years, and I think there will be some cities underwater faster than that. But what say you?
How soon will? Well, like Jim Hansen says, we could have several meters of sea level rise around the end of the century. Might be a few years later. Several meters puts the entire bottom third of Florida, takes it off the map. It's no longer there. It's underwater. Now buildings will be sticking out in freeways or elevated freeways. But of course, they're already raising roads in Miami to take into account daylight flooding. So yeah, it's a real thing. We'll build seawalls around some cities that we can afford it, maybe New York or something where you have the right kind of thing. You can't do it in Florida because Florida is built on porous rock. So you build a seawall, the water just goes underneath the seawall and
let them build seawalls.
Let them build seawalls. So the answer is probably quite a few at this, and it's also something I think even solar radiation management taking steps to cool the Earth right away. It would slow it down. But the oceans are so hot now that there's going to be a lot of sea level, a lot of ice melt. But
yeah, so I was in Panama, and I think in 2009, and there were these Kunayala tribes, these native inhabitants of the islands, and they were. We were going with a wooden ship, with a canoe to collect sand to increase the land there, but they already knew that it was too late. They were already preparing to move to the mainland of Panama, and that's what they're now doing already. You see big communities move from the islands in the what is that the north of Panama, the Caribbeans. I think that's maybe, I don't know the regional seas, but so the Caribbeans, you see these Kunayala people move from these Caribbean islands to the small Caribbean islands to the mainland and live back in the city, and that's, of course, that's also impacting cultures and really changing the ways of life, and yeah, their islands are essentially already lost. So they don't need to be below sea level 24/7, but the waves increase, the strength of the waves increase, the sea level rise gradually just eats away from at these islands, and that's happening all around the world. So the lower level islands, and they need the islands that are built from less strong material, porous rocks or sand or this volcanic stones. Those are already disappearing quite fast, and yeah, like my country will most likely be gone within 1 or 2 centuries, where it depend for a large part, depending of course on how much money we invest to build indeed seawalls and to pump out the water. We've been doing that for a while, but yeah, it can't last forever, I think.
What I wonder what Shell thinks of that, since they're your
They just care about
hometown
the short-term
heroes.
profits.
Yeah,
Yeah.
they moved to the UK. They don't give a shit.
Oh, they did. Oh, okay. Another one is the if you could talk about the role and scale of land use impacts on biodiversity and climate, and how to integrate these biodiversity and climate land use impacts into policy.
Sorry, can you repeat?
About land use policy. And biodiversity. The role and scale of land use impacts on biodiversity and climate, and how to integrate these biodiversity and climate land use impacts into policy. I'm guessing to prevent all the things that are going on, but we're not doing a lot of it. So, I mean, none in the video, you showed.
Yeah, I don't know if this is focused on a certain region or globally. Of course, there's a lot of answers to give here. My wife is an ecologist, and so I know through her I know quite a bit about what's needed to improve the regional ecology, and that's not creating these huge like homogeneous, like only one species of crops, monoculture crops, because that's an ecological desert. Netherlands is, if you fly over it, if you don't know what you see, you might think, oh, what nice and green pastures, but those are quite dead. It's all like imported species of English grass, which is high production grass for our cows and cattle and for milk production. And so yeah, I think that restoring ecosystem is really crucial. And I think there's some opportunities to, of course, to reduce meat consumption, to reduce milk, to reduce production of crops for animals to eat, and then to because you lose a lot of energy and nutrients along the value stream, of course. And also to just improve also nutrition, because it's we can get a lot more nutrition from our foods if we do it better, and then that could also help to improve the ecosystems and possibly also to reduce the climate impacts of agriculture. Then there's some who keep campaigning for just have more cattle, wild roaming cattle, because that decreases or that could help the agricultural or the nature to restore carbon. But I think that's bullshit, literally bullshit.
Yeah.
Yes, indeed.
So
there was another question about from one of our favorites, Nadia. Is warming about to abruptly speed up? How far, how fast? Is there any notion of what the human impacts might be yet?
this is kind of a summary of everything we've been talking about in a way. So it's a good, maybe a good place to end, and by kind of going over it. Aren't we seeing an abrupt temperature increase in the last 2 years and continuing into this year, and maybe regional impacts in the Mediterranean? Do you expect that this year?
Yeah, so we already see it indeed and that's also was the point of the European Geosciences Union comment, which I shared, which said that we will see it first in the Earth's energy imbalance, and we see the Earth's energy imbalance is still increasing, which means that the heat accumulation globally is still increasing. Of course, this can be like a few months a dip and then an increase again. But if you look at the trend, we still see the trend going up. We still see, and that's from the satellite data, that's from the ocean heat content data, that's from the sea level data, where you see the sea levels increasing faster and faster, and much of that being due to the expansion of the ocean, the heating of the oceans. And that is translating to more and more record temperatures, and that also increasing rate of warming regionally, and especially regionally where most of us live. And I cannot stress that enough, because these emissions, the air pollution that was keeping us relatively cool was all centered over the area where we were burning stuff. It's not rocket science. We were burning stuff that was keeping us cool, and we were doing that over the regions where we were doing that, right? And then if we stop doing that for our health, for understandable reasons, that will cause more warming in these same regions. And that's also where most of us were fishing, like where our fish were caught in the Atlantic and in other seas where even these shipping vessels now have to burn low sulfur fuel, of course, and all the other ships that are going there. So yes, we are seeing, it's not that we will, but we are seeing rapid accelerated warming, and there's, as I showed with this graph, where the imbalance is still in this region is still 2 watts per square meters higher than at the start of this century. So that will result in a lot more warming, like because it's I don't even see this band narrowing yet, which would need to see for the rate of warming to start maybe leveling off. So yeah, I don't know.
So the answer is yes. Near-term warming expected, especially regionally if you're in Europe, India. The U.S. has been cleaning up its sulfur for a long, long time. China is now in the process of cleaning up its sulfur significantly.
Well, my graph was including it. It was my graphing. Where is it? My graph included the U.S. So don't.
Mm-hmm. Oh, well, the one with the band. Yeah.
Don't forget the U.S. These seas. If these seas were kept cooler than they were before, that also helped to keep the United States cooler than it was before. And of course, there's regional differences, and so it's a bit of this is like 73 million square kilometers, 14.3% of Earth's surface. So it's quite a big area, but it's regional experience might differ. I think that's always a good disclaimer.
Yeah, and the shipping, of course, is heating up the water, and that's.
And the water is heating up the atmosphere and evaporating water, and bringing all the rain.
Is this going to be a cruel summer for the Mediterranean?
Yeah, well, I think last year there was a zeta joule. I think I don't remember. I calculated it was like 17.5 million Hiroshima bombs of heat accumulated in the Mediterranean in 1 year, and that was before this additional desulfurization. So yes, again, one country might experience it more than another, but you've seen what happened in the past years, where a third of Greece was underwater, and Spain had these extreme flooding, and Libya. So all these different countries around the Mediterranean and near the Mediterranean are already experiencing more and more extreme weather. Turkey, and I've been on CNN Turkey to talk about this, and it will. Like I predicted it would happen, and now we saw that like in the past 15 years, there's more warming than in these regions than in the preceding 150. So it's a lot, and I don't see any indication that it will get better, or even that the rate of change will start to decrease anytime soon.
Any predictions on when mainstream climate science will accept this explanation? I mean, in a year?
Well, at least they started to talk about it. I think that's something that we help to initiate it somewhat. That they start to take it more seriously, and like what is mainstream, right? Those, and I thought I tried to show you that those who are looking at the data are already saying like this. These changes are very rapid, and we need to start taking this serious, because it's already NASA and NOAA and many others are highlighting that the rate of warming has more than doubled. So and those, like if you ask me, those are the real mainstream scientists who just look and present the data as it is. And of course that there are people who the media really likes, who say that things are not that bad. But yeah, if they are lying to you because they want to sell books, we've talked about that before, and people want to buy into that hope, I understand that. But if it's countries that are at stake here, there's many countries that are at stake here, and civilizations, different civilizations, the coral reefs are at stake here. So we really don't need much less false hope and more reality, and taking the observations, as I show here, taking the observations serious.
Mm-hmm. Okay. Whoop. Let's see.
Yeah.
Oh, right. You're sharing. So as long as you're sharing, that's going to happen. I think we've covered a lot of it today. I mean, still some questions there, but we'll cover them in future things. Leon, thank you so much for educating all of us on some of the latest research out of the EGU, and especially on your own research, of course, with Jim Hansen, and the part that's not being focused enough on by the mainstream media. But we're living it in real time, so we'll all get to experience all these changes. We have lots of exciting rooms coming up in the future. Please like and subscribe. We don't push it enough here like other channels do. However, we're talking about climate information, and the more that this information reaches people, the better the positive impact it can have. And you can do your part by basically liking and subscribing and telling others about the channel. So please do that, and it will help us all. And I mean all, because climate communication, having the scientific information is one thing, but getting it out to the public so that they understand it and demand action, that's a whole other thing. That's the part that we're really having trouble with. So anyway, thanks everyone, and thanks everybody, and Stacy and Eli, and especially Leon.
Yeah.
And we will see you next time. Oh, yes.
May the 4th be with you.
Oh, very good. Okay.
Yeah.
Everyone, and we'll see you next time. Thanks, everyone. Bye-bye.
Bye-bye.
Bye.
Well, let me go out with the title slide. There we go.